Good evening, Internet. I am Matt Booyak, and in this video, we'll take a look at the 27th problem from the Project Euler problem archive. Now, this problem makes an observation about a particular quadratic expression, and it notes that if we evaluate this expression for non-negative consecutive integers starting at 0, we get a sequence of prime numbers. And our goal for this problem is to see if we can find a similar quadratic expression that produces a longer sequence of primes, the longest such sequence in particular. It notes that our expression should be of this form, and it gives restrictions on the range of values for A and B. So my first instinct when looking at a problem like this is to note that finding prime numbers in general tends to be a brute force affair. That is, the prime numbers tend to behave fairly randomly. And so typically, problems involving prime numbers, you end up having to resort to brute force. Fortunately, in this case, our search space is not particularly large. As I mentioned, the parameters A and B range from -1,000 to +1,000. And we can expect that most quadratic expressions of this form are going to have either 0, 1, or 2 primes in their sequence. That is, most are going to hit a composite number very quickly. And so our search space is probably in the 4 million or 5 million range, something like that. Okay. The other thing that I would notice looking at this problem is that we only have 2 degrees of freedom. That is, our quadratic term is required to be or to have a coefficient of 1. And what this means is that as soon as we know the first 2 values of our sequence, that defines the entire parabola. And I'll show you how we can solve for that in just a moment. But that means that if we pick the first 2 values to be primes, we can calculate the corresponding values of A and B. And then instead of having to try all these different values of A and B, we're just trying prime numbers. And I've mentioned in a number of videos that there's a theorem, prime number theorem, which looks at the number of prime numbers less than a given number and says that there's a very good approximation for that value of n over the log of n. And so that is the natural log of n. And so if we suppose that our prime numbers could be as large as 2,000, for example, we're doing 2,000 over the natural log of 2,000. That's 263. Say square that. You're looking at 70,000 as our search space rather than 4 million. And I'll in a moment give justification for that range. We'll see that the restrictions on A and B also put restrictions on the values of our primes. Okay, so with that out of the way, let's get into it. As usual, we'll copy our template directory to make our problem directory. And let's open up our analysis file. Okay, so I mentioned that given starting primes, say P and Q, we could calculate values A and B. So let's just say, recall f of n is going to be equal to n squared plus an plus b for 1,000 less than a comma b, negative 1,000. Less than 1,000. Now this is actually I've simplified this slightly. Technically, B is allowed to be 1,000, but we'll see that, or negative 1,000, but we'll see that neither of those is actually possible in just a moment. Okay, so let's suppose P and Q are primes, and f of 0 is equal to P, and f of 1 is equal to Q. So that's going to give us 0 squared plus A times 0 plus B is equal to P, and 1 squared plus A times 1 plus B is equal to Q. So that's going to give us P is equal to B. Rather, the other way around, we want B is equal to P. And then we're going to have A is equal to Q minus B minus 1. And we know that B is equal to P, so we can just stick that in there. Oh, that should be A. There we go. Yes. Okay, so now we can see that, as I said, given starting primes P and Q, we can calculate the rest of the parabola. And we'll just say, note, B, well, first of all, B has to be a prime. That means, positive not equal to 1,000. So this justifies my, my simplification up here. And then because P has to be, rather B has to be, prime between 0 and 997, that lets us put limits on A as well. So you'll see if P here is has to be yeah, because P has to be less than 1,000, that means that and A has to be less than 1,000. We'll notice Q is equal to A plus P plus 1. And we have, A less than 1,000, P less than 1,000. And so we have Q is less than P plus 1,000. Okay. The other thing that I'll note is that rather than calculating our parabola every time, there's actually a way of efficiently calculating consecutive values of a parabola. And in particular, if we take 3 consecutive values and we find the difference between the first and the second and the third, the difference between the differences will be constant. And so let me just show that real quick. Suppose we find f of n plus 1 minus f of n. And so that's going to be n squared, n plus 1 squared plus a n plus 1 plus b minus n squared plus minus an minus b. And so that's going to give us 2n plus a, yes, plus 1. Yes, that should be correct. Okay. And so now if we do f of n plus 2 minus f of n plus 1 minus f of n plus 1 minus f of n. That's going to give us 2n plus 1 plus a plus 1 minus 2n plus a plus 1, which is going to be equal to 2. And so you can see that this is constant. The difference of the differences for consecutive values is going to be constant. And so this means to find each additional value in the sequence, just add 2 to diff and add diff to the current value. Okay, so I think that should be just about everything we need to get started on our solution. So let's open up our main.cpp. Okay, so we're going to need to pull in primes.h, and that will mean that we need to link our number theory library. If you're not familiar with this, I had a whole series of videos on prime numbers and calculating prime numbers, and so you may want to check that out if you haven't seen that yet. And then I'm also going to include utilities.h. And so this includes this superlatives class, which is useful for tracking the best answer. If you're supposed to consider a number of possibilities and find the best solution to a problem, this class is one that we wrote in a previous video that's useful for doing that. And let me just pull up the primes class real quick. So we'll just be using get prime and is prime, just basic prime functionality there. Okay, so let's get started. So you'll recall that the superlatives class requires us to have a state structure. So we'll just call this problem 27 state, and then that's just going to be A and B. So then we're going to have our superlatives, and it's going to have state of problem 27 state, and the value is going to be a uint32t. That will be the length of our sequence. All right, we'll also need we'll need some indices for our to indicate the current prime that we're considering, as well as the length of our current sequence. We're going to need our current primes. We're going to need the diff and the value of our current value of our function. Let's just call that cur. I think that's probably everything. All right, so let's say I is going to go from 0. We want, we need our primes class. So we're going to say p dot get prime I is less than 1,000 plus I. And then we'll say p equals p dot get prime One note about the way that this primes class works, the entire purpose of it is to cache primes that we've calculated. And so this is basically free. This second call to get prime I, we're not actually recalculating that prime. The primes class will have already calculated that and stored that for us. Okay, so now we're going to go from j is equal to 0, and j is, or p dot get prime j is less than p plus 1000, and plus j. And q is equal to p dot get prime j. Okay, so now we need to evaluate how many primes we have in the parabola, which corresponds to p and q. Okay, so we'll want to say diff is equal to q minus p. And we're going to start with the length is equal to 1. And that's because the way our loop here is going to work is that at this point we don't know if... we also want to set cur equals q. We don't know if cur is prime or not. We do in obviously when we're starting because we've chosen it to be prime. But after the first iteration, we won't know if cur is prime at this point. So we want to say while cur is greater than 0 and p dot is prime 32t cur. You'll notice I'm trying to be careful about which values are signed and which values are unsigned. Our primes class works entirely with unsigned values, but because of the way our parabola is defined, it's possible for us to have negative values, and so everything, all of the the parameters for our parabola are all signed integers, but the primes class works with unsigned integers. Okay, so let's do diff plus equals 2, and length, or plus length, and then we're going to do cur plus equals diff. Okay, so at this point we've calculated the length of our sequence, so we can say super.add_state, and this is going to be a problem 27 state. And so our value for A, let's go back to our analysis. We're going to have A is Q minus P minus 1. So we'll say Q minus P minus 1. And then B is just going to be equal to P. Okay, and then here we can say struct const problem 27 state reference state is equal to super.maxState. And then we can just say printf A equals %d, B equals %d, length equals %d. And so that will just be state.a, state.b, and super.maxVal. Okay, looks like we have a small mistake. Yes, I've just forgotten to add our length. Cannot find, we'll need to build No, the library's up to date. Oh, yes, I've just made a minor syntax error. Okay, so we have a candidate solution here. Before I pull that up and check to see if that's correct or not, there is one more thing that I would like to say about this problem. I actually did a fair amount of analysis in preparation for this problem, trying to find some kind of clever solution that didn't require brute force. And I wasn't successful in that regard, but I did make some interesting discoveries along the way. One of them is if you have a sequence of prime numbers generated by a parabola, you can shift that parabola to the left and also have a sequence, a shorter sequence of prime numbers. Or if plugging -1 into your parabola gives you a prime number less than 1,000, you can shift your parabola to the right and add that one to your sequence. And something interesting happens if you start shifting the examples that they give in the problem statement. And in particular, if you take, let's see, where is it? This parabola here, and you shift it just a little bit to the left, so you'll notice that this value is not legal. We're only allowed to have values up to 1,000, and so this example is not a legal example. But if you take this and shift it to the left until this value drops below 1,000, you actually get this this parabola here, our solution. If you continue shifting this example farther to the left, you will eventually get this parabola. And so it turns out that, assuming our solution is correct, not only do they give you the answer to this problem in the problem statement, they actually give it to you two different ways. And so it actually turns out that this problem is really kind of stupid. There's nothing interesting to be discovered beyond what they've already told you in the second line of the problem statement. And so I have to admit that this was a little bit of a disappointment when I discovered this. But in any case, let's take a look and verify that our solution is indeed correct. Oh, I've missed a step. In order to actually get our answer, we need to multiply -61 and 971. There we are. And you'll see that this matches the archive. So that's the end of that problem. We'll look forward to solving problem number 28 in the next video.